The impact of Cynthia Dwork on differential privacy. Cynthia Dwork is a luminary in the realm of data privacy, particularly recognized for her groundbreaking contributions to the concept of differential privacy. This innovative framework emerged as a response to the pressing issues surrounding the privacy of individuals' data amidst the growing capabilities of data collection and analysis. The journey of differential privacy began in earnest in the early 2000s, with Dwork's foundational work paving the way for a robust approach to protecting individual privacy in statistical databases. Historical context and motivation. The roots of differential privacy can be traced back to the 1977 work of Tamara Dalenius, who articulated a crucial principle for statistical databases: nothing about an individual should be learnable from the database unless it could be inferred without accessing the database. Dwork and her collaborators identified an inherent impossibility in formalizing Dalenius's goals strictly through semantic security, leading them to develop differential privacy as a more practical alternative. Dwork's research highlights the paradoxical nature of privacy. Even individuals not present in a database could have their privacy compromised. This revelation underscored the need for a framework that could quantify privacy risks associated with data sharing and analysis. Defining differential privacy. Differential privacy is defined as a mathematical guarantee that a database query's output will not significantly change when a single individual's data is altered. This concept effectively encapsulates the idea of privacy risk incurred by participation in a data collection process. The introduction of noise into data analysis, where random variations are added to query results, ensures that individual contributions remain obscured, thus protecting personal privacy. Dwork's work, particularly through collaboration with Aaron Roth, culminated in the publication of the Algorithmic Foundations of Differential Privacy, a comprehensive text that delineates the theoretical underpinnings of differential privacy and practical methodologies for its implementation. This book serves as a cornerstone for understanding the techniques that achieve differential privacy across various contexts, such as query release problems and machine learning applications. Theoretical foundations and techniques. Dwork's research has led to the establishment of several key principles and algorithms that underpin differential privacy. One of the notable contributions came in 2006 when she co-authored a paper on calibrating noise to sensitivity in private data analysis. This work introduced essential techniques for determining the appropriate amount of noise to add to a dataset based on the sensitivity of the queries being asked. Sensitivity refers to the maximum change in the output of a function when a single individual's data is altered. And calibrating noise to this sensitivity ensures that privacy is preserved while maintaining data utility. The literature surrounding differential privacy emphasizes its versatility and robustness against adversaries with arbitrary computational powers. Dwork's discussions extend beyond static databases, addressing the challenges of preserving privacy in distributed databases and data streams, thereby expanding the applicability of differential privacy in increasingly complex data environments. Practical applications. Differential privacy has found applications across diverse fields, including healthcare, finance, and social sciences, where privacy concerns are paramount. For example, organizations can use differentially private algorithms to analyze sensitive patient data while ensuring that individual identities remain confidential. Similarly, companies can leverage differential privacy in their data analytics and machine learning models to derive insights without compromising customer privacy. Dwork's work has catalyzed a philosophical shift in computational privacy goals, illustrating that by rethinking traditional approaches to data analysis, significant improvements in privacy-preserving outcomes can be achieved. Rather than merely adapting existing algorithms to be privacy-preserving, researchers and practitioners are encouraged to innovate new algorithms that inherently incorporate differential privacy principles. Challenges and limitations. Despite the remarkable advancements enabled by differential privacy, Dwork and her colleagues acknowledge that there are inherent limitations. The balance between privacy and data utility is delicate. Overly stringent privacy guarantees can render the data too noisy for meaningful analysis. This trade-off necessitates ongoing research and development of algorithms that optimize both privacy and utility. Moreover, the computational complexity associated with differentially private algorithms varies significantly. While some algorithms are efficient, others may require intensive resources, which can limit their practicality in real-world applications. Dwork's exploration of the computational aspects of differential privacy provides a framework for understanding these challenges and identifying potential solutions. Conclusion: Cynthia Dwork's contributions to differential privacy have profoundly influenced the landscape of data privacy, establishing it as a standard approach for protecting individual information in an increasingly data-centric world. Her work not only addresses the theoretical challenges of privacy in statistical databases but also lays the groundwork for practical implementations that are both secure and efficient. As the digital landscape continues to evolve, the principles of differential privacy will remain crucial in guiding researchers, policymakers, and technologists in their efforts to safeguard personal data. Dwork's pioneering work serves as a beacon for future advancements in privacy-preserving data analysis, ensuring that individuals can participate in data-driven initiatives without fear of compromising their privacy. Cynthia Dwork's work on differential privacy presents several counterintuitive insights that challenge common perceptions about data privacy and analysis. Here are some of the key counterintuitive points drawn from her research and related literature. 1. Impossibility of perfect privacy. One of the most striking revelations from Dwork's initial work is the impossibility result regarding the formalization of privacy in statistical databases. This contradicts the intuitive belief that it might be possible to create a system where no information about individuals can be gleaned without access to the entire dataset. Dwork's findings indicate that even the existence of aggregate data can threaten individual privacy, suggesting that full privacy might be an unattainable goal. 2. Risk from participation. Dwork's research highlights that individuals who participate in a database may inadvertently increase their risk of privacy breaches. This is counterintuitive because one might assume that only those whose data is included in a dataset are at risk. Dwork demonstrates that even those not represented can be affected due to the nature of statistical inference, where the presence or absence of a single individual's data can reveal sensitive information about them. 3. Noise calibration for privacy. The concept of adding noise to data queries to protect privacy leads to another counterintuitive insight. Sometimes introducing randomness can lead to more accurate aggregate results. This challenges the conventional understanding of accuracy in data analysis, suggesting that a careful calibration of noise can yield insights that are both private and useful. Contrasting with the traditional view that noise inherently degrades the quality of data. For privacy versus utility trade-off, there is a common belief that increasing privacy must come at the expense of utility. However, Dwork's work illustrates that this trade-off can be managed more effectively than initially thought. By rethinking the computational goals and employing techniques that cleverly integrate privacy-preserving measures, it is possible to achieve high levels of privacy while still maintaining significant utility in the data analysis. This challenges the perception that privacy must always diminish the usefulness of the data. 5. Adversarial power. Dwork's framework for differential privacy maintains that the algorithms are robust against adversaries with arbitrary computational power. This is counterintuitive because it suggests that even sophisticated and powerful attackers cannot easily compromise the privacy guarantees provided by differentially private mechanisms, which runs contrary to the assumption that stronger adversaries will inevitably find ways to breach privacy. 6. Versatility of differential privacy. While many might assume differential privacy is only applicable to static datasets, Dwork's work extends its applicability to dynamic contexts such as distributed databases and data streams. This expands the potential for employing differential privacy in real-world applications beyond what was originally conceived, highlighting that privacy can be preserved even in complex data environments. 7. Creative combinations for better outcomes. The proposition that combining differentially private techniques can yield better results than simply adapting existing methods is another counterintuitive finding. It suggests that innovation in privacy-preserving algorithms can lead to more effective solutions than straightforward adaptations, urging researchers and practitioners to think outside the box when designing privacy-preserving mechanisms. 8. Static versus dynamic models. The conventional wisdom might suggest that privacy mechanisms should be designed for static databases only. However, Dwork's framework indicates that dynamic and adaptive approaches can also be built around differential privacy principles, showcasing the flexibility of the approach and addressing privacy concerns in various contexts. 9. Algorithmic complexity. There is a common assumption that all privacy-preserving algorithms are computationally intensive, but Dwork's findings reveal that some differentially private algorithms can be quite efficient. This complicates the narrative around privacy-preserving methods, suggesting that effective privacy solutions do not always require significant computational resources. These insights illustrate how Dwork's contributions to the field of differential privacy not only advance technical understanding but also challenge and refine existing notions about data privacy and analysis, emphasizing the need for a nuanced approach to privacy in the age of data. Cynthia Dwork's work on differential privacy has fundamentally reshaped the field of data privacy, yet there are several important aspects of her contributions that are often overlooked or underappreciated by many, even those familiar with the subject. Here I will highlight these critical elements and explain their significance. 1. The evolution of differential privacy from theoretical foundations. While many recognize differential privacy as a practical tool for protecting individual privacy in data analysis, the theoretical underpinnings of this framework are less often discussed. Dwork's early work began as a response to the limitations of traditional privacy measures, particularly the impossibility results she presented regarding formal privacy guarantees. The significance of this evolution cannot be overstated. It underscores the necessity of developing a new privacy paradigm that does not merely aim to protect data but provides a mathematically sound framework that captures the inherent risks associated with data sharing. This foundational shift laid the groundwork for future advancements in privacy-preserving data analysis. The realization that privacy cannot be perfectly guaranteed, especially in a world where adversaries may possess arbitrary computational power, highlights the importance of creating frameworks that allow for quantifiable privacy risks. As such, the discussions around impossibility results serve as a crucial reminder of the limitations of previous approaches and the need for innovative solutions in the face of increasing data collection and analysis capabilities. 2. The role of noise calibration. Dwork's work on noise calibration is another aspect that is often underappreciated. The 2006 paper where Dwork and her collaborators introduced the concept of calibrating noise to the sensitivity of queries is vital for practical implementations of differential privacy. The significance of this work lies in its practical applicability. By understanding how much noise to add based on the sensitivity of the data being queried, practitioners can achieve a delicate balance between privacy and data utility. This calibration process is what allows differential privacy to be both rigorous and practical, ensuring that while individual data points are obscured, the overall findings from the database remain valid and useful. Many discussions around differential privacy tend to overlook the technical intricacies involved in implementing these algorithms effectively in real-world scenarios. Understanding noise calibration is crucial for developers and analysts who wish to apply differential privacy in practice, as it directly impacts the quality of the output data. 3. Applications beyond static databases. Another critical aspect that often goes unnoticed is Dwork's exploration of differential privacy in dynamic and distributed environments. While much of the early literature focused on static databases, Dwork's work extends this framework to more complex scenarios such as data streams and distributed databases. This transition is significant because it reflects the realities of modern data environments, where data is not only vast but also continuously changing and being shared across different platforms. The implications of applying differential privacy in these contexts are profound. It indicates a shift in how privacy can be preserved amid the complexities of real-time data analysis and sharing. This expansion of the differential privacy framework is essential for ensuring that as technology evolves, privacy measures can adapt accordingly. It also opens up a range of new applications for differential privacy that can be critical in fields such as online social networks, healthcare, and financial services, where data is often distributed and dynamic. 4. The philosophical implications of differential privacy. Dwork's work also invites a philosophical reflection on the nature of privacy itself. Many discussions about privacy focus on individual rights and the ethical implications of data misuse. However, Dwork's approach shifts the conversation to the computational goals of privacy-preserving algorithms. By redefining the objectives of data analysis in light of privacy considerations, Dwork challenges practitioners to rethink how they approach data collection and usage. This philosophical aspect is significant because it encourages a broader discourse around data ethics and privacy, prompting organizations to think critically about their data practices. The idea that better privacy outcomes can be achieved not by merely adapting existing methods but by fundamentally rethinking the computational goals is a powerful insight that can lead to more innovative and effective privacy solutions across various domains. 5. The utility-privacy trade-off. Many in the data analysis community may overlook the nuanced trade-offs between utility and privacy that Dwork emphasizes. While differential privacy enables a significant level of privacy protection, it is essential to recognize that this often comes at the cost of data utility. The balance between these two factors is a recurring theme in Dwork's work, and understanding this trade-off is crucial for anyone involved in data analysis. This trade-off is particularly relevant in sectors where data utility is paramount, such as healthcare and public policy. For instance, when analyzing patient data, ensuring high levels of privacy may reduce the granularity of insights that can be drawn from that data. This is why Dwork's exploration of how to maximize utility while maintaining privacy is vital. It provides guidance on how to navigate these complex decisions in practice. Conclusion. Cynthia Dwork's contributions to differential privacy go far beyond the surface-level understanding of the concept as a tool for data protection. By examining the theoretical foundations, practical implementations, dynamic applications, philosophical implications, and utility privacy trade-offs, we can gain a deeper appreciation for the significance of her work. These elements are critical for advancing the conversation around data privacy in an increasingly data-driven world and ensuring that privacy measures evolve to meet the challenges posed by modern technology. Understanding these facets of Dwork's work is essential for anyone aiming to apply or engage with differential privacy in a meaningful way. 1. Foundational concepts of differential privacy. Cynthia Dwork's work introduces a rigorous mathematical framework for understanding privacy in data analysis through the concept of differential privacy. It provides a formal definition that quantifies the privacy loss when an individual's data is included in a dataset. The inability to achieve perfect privacy, as highlighted in Dwork's research, underscores the necessity of a balance between data utility and privacy protection. This foundational concept has reshaped how researchers and practitioners approach the challenge of data privacy in an era of increasing data availability and computational power. 2. Practical applications and algorithmic techniques. Dwork's contributions extend beyond theoretical foundations. They encompass practical implementations of differential privacy across various contexts, including query release problems and machine learning. The collaborative work with Aaron Roth, particularly in their book, The Algorithmic Foundations of Differential Privacy, showcases a range of algorithms designed to preserve privacy while maintaining data utility. The emphasis on creative combinations of these techniques illustrates that improving privacy outcomes often requires rethinking computational goals rather than merely adapting existing algorithms. This has significant implications for industries reliant on data analysis such as healthcare, finance, and social sciences. 3. Versatility across data environments. Dwork explores differential privacy's applicability not only to static databases but also to more complex data structures, including distributed databases and data streams. This versatility indicates a paradigm shift in privacy preservation strategies, allowing for the analysis of dynamic and continuously generated data while safeguarding individual privacy. This aspect is particularly relevant as organizations increasingly move towards real-time data processing and analysis, necessitating robust privacy mechanisms that can adapt to evolving data environments. 4. Theoretical limitations and future directions. While Dwork's work has established differential privacy as a gold standard for privacy-preserving data analysis, it also acknowledges inherent limitations, both in terms of what can be achieved with differential privacy and with any privacy-preserving method. Understanding these boundaries is crucial for researchers and practitioners as they navigate the complexities of privacy in data analysis. Future research may focus on enhancing the efficiency of differential privacy algorithms, exploring new applications, or addressing the challenges posed by adversaries with advanced computational capabilities, thereby continuing to evolve the field of data privacy. These points provide a comprehensive overview of Dwork's contributions to differential privacy, highlighting its theoretical foundations, practical implications, versatility in data environments, and the ongoing challenges in the pursuit of effective privacy solutions. 1. The Cambridge Analytica scandal 2016. This case involved the unauthorized harvesting of personal data from millions of Facebook users without their consent to build psychological profiles for political advertising. The scandal highlighted significant privacy violations and raised questions about consent and data protection, leading to widespread scrutiny of data practices and regulations on data privacy. This situation stressed the importance of protecting individual data in a digital age. Paralleling the motivations behind Cynthia Dwork's work on differential privacy. 2. United States versus Microsoft Corporation 2001. This landmark antitrust case involved allegations that Microsoft had engaged in anti-competitive practices to maintain its monopoly on personal computer operating systems. The case not only dealt with issues of competition but also raised privacy concerns regarding user data monitoring and collection practices by software companies. The outcome emphasized the necessity for regulations that protect consumer rights, including privacy, mirroring the principles of differential privacy that aim to safeguard individual data in the face of powerful data analytics. 3. HIPAA Regulations 1996. The Health Insurance Portability and Accountability Act established national standards for the protection of individual health information in the United States. It aimed to ensure patient privacy and the security of health data, preventing unauthorized access and misuse. HIPAA's emphasis on data privacy and security resonates with the foundational concepts of differential privacy, which seeks to protect individual data from being identifiable in aggregate datasets, showing the growing recognition of privacy rights in the field of personal data management. Future outlook on differential privacy and Cynthia Dwork's contributions. Cynthia Dwork's pioneering work in differential privacy has profoundly impacted the way we think about data privacy in an increasingly data-driven world. As we look to the future, several trends and predictions emerge regarding the evolution of differential privacy, its applications, and its implications for society. 1. Wider adoption across industries. As awareness of data privacy issues continues to grow, organizations across various sectors, healthcare, finance, education, and government, are likely to adopt differential privacy frameworks to comply with regulations and safeguard individual data. The increasing number of privacy regulations, such as GDPR in Europe and CCPA in California, will drive this trend. Companies will seek ways to leverage differential privacy to not only protect user data but also to extract valuable insights without compromising privacy. 2. Integration with machine learning and AI. Differential privacy will increasingly be integrated into machine learning and artificial intelligence frameworks. As algorithms become more sophisticated, the need for privacy-preserving techniques that allow for the safe sharing and analysis of sensitive data will grow. Future innovations may focus on developing differentially private models that perform well in real-world applications while maintaining user privacy. This could lead to the creation of standard practices for implementing differential privacy in AI training datasets, ensuring that models learn from data without exposing individual information. 3. Advancements in technology and methodology. The field of differential privacy is poised for technological advancements, including the development of more efficient algorithms that require less computational power while providing stronger privacy guarantees. Researchers will likely explore new mathematical frameworks and noise calibration techniques to improve the robustness of differentially private systems. Enhancements in hardware and software capabilities could make real-time differential privacy feasible, allowing organizations to analyze data streams on the fly without sacrificing privacy. 4. Personalized privacy solutions. As users become more aware of their data rights, there will be a push for personalized privacy solutions that allow individuals to control how their data is used. Future applications of differential privacy may include user-configurable privacy settings where individuals can define their privacy preferences while still benefiting from data-driven services. This shift towards personalized privacy could empower users and build trust between them and service providers. 5. Cross-domain applications. The principles of differential privacy will extend beyond traditional data analysis to new domains such as Internet of Things, IoT, smart cities, and autonomous systems. In these areas where vast amounts of sensitive data are generated continuously, differential privacy will be crucial in ensuring that individual privacy is maintained while still enabling collective insights. For instance, urban planners could leverage differentially private data to inform decisions about city infrastructure without exposing personal information about residents. 6. Ethical and societal considerations. As differential privacy becomes more prevalent, ethical considerations will come to the forefront. Discussions around the balance between data utility and privacy, the potential biases in differentially private algorithms, and the societal implications of widespread data collection will be critical. The future will demand interdisciplinary collaborations that include ethicists, social scientists, and technologists to navigate these challenges and ensure that differentially private solutions are equitable and just. 7. Regulatory frameworks and standards. The emergence of differential privacy as a standard practice will likely lead to the establishment of regulatory frameworks and certification processes. Governments and international bodies may create guidelines for implementing differential privacy in various sectors, ensuring that organizations adhere to best practices. This could foster a more uniform approach to data privacy across jurisdictions, enhancing global cooperation on privacy standards. 8. Education and workforce development. The growing importance of differential privacy will necessitate educational initiatives aimed at equipping the workforce with the necessary skills to implement these techniques effectively. Universities and training programs will likely incorporate differential privacy into their curricula, producing a new generation of data scientists and privacy professionals adept in privacy-preserving technologies. Conclusion. Cynthia Dwork's contributions to the development of differential privacy have laid the groundwork for a transformative approach to data privacy. As we advance into the future, the principles of differential privacy are set to become integral to how organizations collect, analyze, and share data. The interplay between technological innovation, regulatory frameworks, and ethical considerations will shape the landscape of data privacy, ensuring that individual rights are upheld in an increasingly interconnected world. The predictions outlined here reflect a trajectory that not only embraces the technical advancements of differential privacy but also prioritizes the protection and respect of individual privacy in the digital age.